Uh, Good afternoon, dear colleagues. Today I'm going to give a presentation on high frequency, on the theta spot and high frequency noise results measured within the frequency interval from 250 MHz to 10 GHz in epitaxial graphene grown on sapphire. I will also provide the comparison with similar results in epitaxial graphene grown on sapphire by chemical vapor deposition. I will basically focus on experimental investigation and its interpretation. Let's start with applications of graphene. As you probably know, graphene is widely used in gas sensing, touchscreen displays, even to desalinate water, as well as in nanoelectronics. Here is an example of graphene field effect transistor on silicon carbide. It has been reported lately by IBM group that the record current gain cutoff frequency exceeds 300 GHz and is comparable to that of the fastest nitride-based field effect transistors. It's worth noting that cutoff frequency is related with average drift velocity and energy relaxation time in graphene channel. This is our graphene structure. Silicon face of a 4H silicon carbide semi-insulating substrate having a lightly n-doped epitaxial layer was graphitized by heating between temperatures 1400 to 1500 for 1 hour at ultra-high vacuum. It is estimated that about 7.5 angstrom thick silicon carbide is consumed to make one graphene layer. Typical RFM image is shown below. Few layer graphene grown in silicon carbide was characterized with a Raman microscope equipped with a argon ion green laser, and spectra were collected in 180 backscattering geometry. 2D and G peaks indicative corresponding to graphene were seen. A D peak indicative of defects in graphene was also observed. The D to G peak ratio was in the range of 15-35%, and it can be used to estimate the graphene grain or domain size. Typically, like for graphene is and silicon carbide, the grain size is about 50 nanometers. A few layer graphene was patterned using microlithography and oxygen plasma. A 150 nanometer thick gold was deposited to contact the graphene layer, and the length model structures ranging from 5 to 35 microns were defined to measure the contact resistance between metal and graphene layer. The low Hall field mobility in graphene on silicon carbide was 2,500, and on graphene on sapphire was 600. While the carrier densities were similar. For graphene on silicon carbide, the electron density is 7.5, and in graphene on sapphire, the hole density 6 to 10 to 12 per quadratic centimeter. The total resistance dependence on the interelectrode distance was used to estimate the contact resistance at low voltages. The 46 ohms was obtained for graphene on silicon carbide, while for graphene on sapphire, we were unable to estimate the contact resistance using this method because there was no linear dependence on interelectrode distance. Room temperature, current voltage dependencies were measured up to 20 volts, and voltage pulses up to 100 nanoseconds were applied in order to reduce channel's self-heating effect. The total resistance decreased from 80 to 30 ohm upon applied voltage, and the application of higher voltage led to the sample thermal breakdown. Since the total resistance is the sum of the graphene layer metal contact resistance and the graphene channel resistance, we concluded that the contact resistance decreased with applied voltage, and this led to the superlinear current voltage dependence. Similar characteristics were observed by Chu in exfoliated graphene with gold pads. Now we will introduce the noise technique to study energy dissipation in 2D and 3D channels. When electrons are heated up, fluctuations in the electron's velocities are enhanced and cause stronger fluctuations in the current. These fluctuations emit electromagnetic radiation that is measured with a sensitive radiometer. The emitted signal is detected with a low noise amplifier, and further it is amplified by low noise amplifier detected with microwave diode. The signal is integrated in the gated integrator. The signal is calibrated with the noise generator. The system walkout and background noise is subtracted, and wave modulator alternatively connects either the sample or the noise source kept at room temperature. The background signal is subtracted in the integrator. The sample impedance is also taken into impedance mismatch is also taken into account. This is a scheme of how a noise signal is processed. The application of two-pulse technique introduces the necessity to measure very weak noise signal, 10 to minus 15 times 10 to minus 12 watts, on the background on the strong voltage up to 10 watts. The circuit used to heat the electrons is decoupled from the circuit measure of electron noise. The noise temperature enters the expression for available noise power, where dF is the bandwidth around the radiometer frequency, and K is the Boltzmann constant. The radiometer frequency is said to be 10 gigahertz. This frequency is high enough to avoid low frequency noise sources such as flicker noise and generational combination noise. For low noise measurements, we additionally use Agilent real-time oscilloscope. Later, I will use noise temperature as a noise measure, and in some cases it can be as a measure of the mean electrokinetic energy. Here we see a noise power reflection coefficient measured at 10 gigahertz frequency. It experiences an increase up to 0.4 amperes, and I will use these results to estimate small signal response conductance. According to a resistor model-based formula, one can relate the measured reflection coefficient with the small response conductance. Here we assume that small signal response conductance equals differential conductance. So from these two figures, we obtain the differential conductance dependence on the current, and having integrated the inverted dependence over the current and divided by the channel length, we obtained the current field dependence for graphene channel. Here the contact resistance is eliminated. The current field dependence is sublinear up to 16 kilovolts per centimeter in graphene on silicon carbide, while 5 kilovolts per centimeter by samples on sapphire survived only 5 kilovolts per centimeter. Let's turn back to contact resistance. First, if one takes the voltage drop across the graphene channel obtained earlier from the current field dependence and subtract it from the total voltage, then after dividing the remnant pi by the current, one can plot the contact resistance dependence on the applied total voltage. And it decreases from 40 ohms at 2 volts till 1.7 ohm at 17 volts. The observed bias superlinear current voltage dependence might be also due to potential barrier discussed earlier by Chu. Indeed, one can relate the potential barrier, the contact resistance. The more voltage is applied, the lower the barrier for carriers to pass it, and the lowest contact resistance. Also, the bias-dependent contact resistance was observed for cobalt-deposited graphene, and the one reason for that for graphene channel can be decided by p-n junction. Now let's jump into noise results at 10 GHz frequency. Noise temperature was measured in the direction parallel to the applied electric field, and here we see its dependence on the current and electric field. It increases gradually till 1900 Kelvin, and 1 order by a magnitude lower currents are needed to obtain the same noise temperature in graphene on sapphire, as well as 3 times lower electric fields. Here we see noise temperature measured within the frequency interval from 250 MHz till 10 GHz. If for preliminary interpretation, if we fit noise temperature with a metric function, we found that it follows the so-called 1 divided by f dependence, and for several kilovolts per centimeter electric field, the 1 divided by f so-called dependence makes only 20% for graphene on sapphire, while this contribution is stronger for graphene on silicon carbide. Here is another quantity called spectral density of current fluctuations, or current noise spectral density, which is estimated for noise measured at frequencies up to 3 kilohertz. It follows so-called 1 divided by f dependence. According to McWhorter model, one can represent normalized current noise as a sum of the many Lorentzians, each proportional to the inverted square frequency, and each representing an elementary source of current density fluctuations with its own characteristic time associated with defect trapping levels. The contacts may also play an important role to 1 divided by f noise. So in our case, for graphene, the normalized spectral density from 1 Hz till 10 gigahertz can be plotted as a sum of several Lorentzians and wide noise contribution. The highest frequency Lorentzian has the characteristic time 0.7 microseconds, and the amplitude 3.2 10 to minus 12 hertz. It is worth noting that this Lorentzian can be explained by short noise as a result of contact barrier, contact barrier resistance, which is shunted with barrier capacitance. At 10 GHz, this noise source is eliminated. That's plot spectral density of the dominant white noise at 10 GHz, which is expressed through noise temperature and small signal response conductance, which was estimated earlier from noise power reflection measurements and a resistor model. The results for graphene find themselves below the ideal short noise from correlated passage of carriers through the barriers up to 0.5 ampere. The correlation is often estimated by Fano factor, which is estimated to be 10 to minus 3 in graphene on silicon carbide, but twice lower value was obtained for graphene on sapphire. This suggests a strong anti-correlation. A moving carrier in a barrier reduces the probability for another carrier to enter the barrier region. Summarizing, I can say that noise spectrum is measured in the field direction at room temperature within 250 MHz 2.5 GHz band. A 1 divided by f type dependence is found for graphene and silicon carbide, while Lorentzian type spectrum with characteristic time of 0.7 microseconds was revealed for graphene and sapphire. Short noise dominates at 10 GHz. The low spectral density of short noise is possibly caused by strongly correlated electron hole jumps across the potential barriers located in the graphene layer. The contact resistance is found to decrease with a light electric field as a result of the possible potential barrier between the graphene layer and the metal electrodes. So to make a good ohmic contact in graphene is still a challenge. Thank you for your attention.